In this next video, we're going to take a pretty detailed look at import-export options and best practices for Hadoop. We're going to look at some of the common tools for importing and exporting data into and out of Hadoop. That includes Flume and Scoop, as well as a brief overview of Storm, Kafka, and Kinesis. We'll look at the options side by side and look at where to use one over the other. And also, we're going to look at some best practices for data import and export. First up, we have real-time ingestion and analysis engines. Things like Flume, Storm, Kafka, and Kinesis roughly do the same thing, which involves multiple distributed agents who push and pull data to and from one another. We typically have one agent on each machine, and these agents can do value-added processing like deduping, filtering, and so on and so forth. Although Flume can do value-added processing options, engines like Storm, Kafka, and Kinesis are much richer in the analysis that they can do as you're pulling the data in. These systems are platform agnostic, and they don't care if the eventual sink or the end-up location is Hadoop, a NoSQL engine like Cassandra, or a flat file system on a local file system. For database import and export, we really have one tool available to us, and that is Scoop, or SQL to Hadoop. It's a single process that imports and exports RDBMS data to and from Hadoop. It does no analysis or filtering itself. It's frequently used to move data to and from Hadoop on a periodic basis so that Hadoop can go through and do its batch processing. A Scoop job is often part of an overall Oozie workflow, such as at 2 a.m., maybe we pull all of our orders table deltas from the MySQL online transaction processing system. After the data is pulled, maybe we run the recommendation engine MapReduce job, and then after that MapReduce job completes, we use Scoop to export the data back to MySQL and update our recommendation engine so that users that come back to our site will get updated recommendations. Again, each of these three steps would be an individual part of an Oozie workflow. If we compare and contrast Flume and Scoop, Flume is essentially used to pull data in real time from any system. It was initially created to process log files, and in the Flume basic stack, we walk through its name and how it got it. Flume is one direction. It's only used for ingestion or pulling data into HDFS. Scoop can also export data back out of HDFS. The Flume agents have to be written in Java. They do run in a JVM. However, Flume is very easy to configure, and if we set up just a config file containing maybe 15 lines, we actually need to write no Java code. Scoop is used to import and export data to and from an RDBMS. It can do deltas, such as pull in only the added rows or rows that came in after a specific timestamp. It essentially uses a map-only job to select or insert data from or to an RDBMS. Both of these systems can act as dumping agents into Hadoop, as opposed to these analysis on ingestion systems like Storm, Kafka, and Kinesis. If we compare Flume versus Storm, Storm was essentially built for complex real-time streaming analytics, analyzing data in flight as it's being generated. It was developed by Twitter essentially to process Twitter streams as they occur. It uses worker processes like bolts that can be written in any language. It uses a thrift interface and JSON over standard in and standard out. Flume, however, was mainly built for moving massive amounts of data, essentially log data, from source into destination, and destination is typically a Hadoop system or a NoSQL database. It's extremely easy to configure and use for this purpose. Again, each individual agent probably only needs maybe 10 to 15 lines minimum of configuration. It was developed by Cloudera, and it can perform analysis, but it's not as easy to use as Storm, and Storm was set up essentially for that analysis purpose. The worker agents in Flume have to be written in Java. Again, if you're using standard configuration, you only need to pass configuration files themselves. Both, however, are extremely scalable. You can either add tiers to an individual data flow, or you can add additional agents at a tier to span the system out horizontally. You can use either of these systems to process millions of events per hour. Both are open source, free, and very mature. If we compare Flume versus Kinesis, Kafka, and Storm, Flume again pushes most of the analysis to the batch processing system, like Hadoop. It's ideal for log analysis, where we're just essentially pulling logs in, pumping them into Hadoop, and then Hadoop does the analysis. Kinesis, Kafka, and Storm essentially perform analysis on unterminated data, where the flow of data never ever stops, and data just keeps coming into the system. These systems can also persist data for later analysis, especially Kafka. Flume's whole purpose is to persist that data for later analysis by a batch processing engine like Hadoop. Kinesis, Kafka, and Storm are ideal for projects where fast analysis is required and can sometimes make the differentiator between whether or not your business succeeds. If we take a deep dive into some of the best practices around these import and export tools, one of the first things that you're going to want to consider is using a workflow engine like Oozie. Oozie essentially chains together these pull, analyze, and push operations into repeatable chunks so that we can run many things like pulling the data from an RDBMS, running a series of pig, scoop, or raw MapReduce jobs, and then exporting the data back into RDBMSs. These import-export systems do have some concerns that we need to take into account regarding HDFS. If you remember that HDFS exposes files as the number of blocks that they are written, you can quickly see that unless we put a directory structure into place, our users might be processing data that's not completely finished being input yet. Users could process incomplete files, such as if only 500 blocks out of the total 5,000 were written. To avoid this, we probably want to use a directory structure such as this. And again, this is a directory structure in HDFS. /incoming would be where our data is pumped to while the file is still open. Once all of our blocks are written to /incoming, our upstream process that's putting that data into the system would then move it to a directory like /ready for processing. Once a full file is written, it'd be moved here, and your individual users can know to only point their processing scripts against this ready for processing directory. Finally, if it's important to know that our data was processed, we might want to include something like a /process directory. This would be useful if our input files are typically only processed once. Our processing engine could process it in ready for process, and then once processed could move the data over to the /process directory in HDFS. This would signal future users that this data has already been processed, and they only need to point to the /ready for processing directory. If you remember, systems like Flume and Kafka and Kinesis will just keep writing files and blocks forever. You have to use this 3-tier directory structure if you want to know what is where in the overall processing scheme. Systems like Flume will also create a small files problem in HDFS. If you remember, having a bunch of small files in HDFS obviously creates a problem where it starts looking like random reads. This also burns up unnecessary memory in the name node. There are several ways around this small files problem. One is we could simply use an upstream agent like a Flume agent to limit what gets into HDFS. We could dedupe or filter out certain records so that we only get what we need in HDFS. We could also extend the collection period in Flume to write larger files. Flume can write data, for example, into HDFS in maybe 5-second increments. If we instead expand that increment out to maybe 5 minutes, we'll end up with larger files in HDFS. Probably the best way to deal with these small files that are created is to periodically combine and compact these files and restore them in HDFS as one single large file. This was a pretty in-depth look at the import-export options and overview of best practices for these systems.